Well, hello there. So let's look at doing some phasor circuit analysis. So remember, we're starting off with phasors. That only works if voltage sources and current sources are sine waves, all with the same frequency in the circuit. We're skipping the transient solution because it decays fast enough that we can ignore it. So this is called sinusoidal steady state, which is different from DC steady state because we have sine waves, not constants. And we like this transform because it gets rid of differential equations. So the basic idea is A cosine omega t plus theta transforms to a phasor with a magnitude or amplitude of A and a phase of theta. So we're just copying certain parts of the equation. Omega will come in later too. So remember, here's another way to look at our setup. We've got V naught cosine omega t plus phi, and that can be written as the real part using Euler's equation of an exponential. And so the amplitude and phase come in here, and we get an e to the j omega t, and that real part on one side and the e to the j omega t on the other side, we just kind of push them away, do the problem, and then push them back in so we can go back to a sine wave. Okay, so now we can look at this in terms of a resistor, actual circuit element. So if we have current I, this is in the time domain, I is Im, the amplitude times cosine omega t plus phi, so it is a sine wave, cosine wave, so we can do phasors. And we can use just Ohm's law, V equals IR in the time domain. So we multiply I times R, and we get R times Im cosine omega t plus phi. So that's the basics here, nothing surprising, no real advantage to the phasor domain for resistors. But this lets us talk about the idea of phasors. So the phasor, we go from lowercase v to bold capital V here. V is IR, where I is now the phasor for I, the current phasor. And so R is just a constant R, so V, the phasor for V, is R times the phasor for I, whatever it is. And once we know V and I in the phasor domain, we can calculate this thing called impedance. It's like a generalized resistance, and so we use Z for impedance, because I is used for everything else already. And so Z is our impedance variable, and it's defined like Ohm's law. So V over I, the phasor for V over the phasor for I, gives us the phasor for Z. And for a resistor, it's just R. So no difference between impedance and resistance for resistors. But if we do the same thing for inductors and capacitors, we will get a difference here. And this is where we're going to get rid of differential equations. So remember, there was a table on the previous lecture that went from the time domain to the phasor domain, and the derivative of a function is j omega times that function. So in the time domain, we've got an inductor, we've got current, I, we've got voltage across the inductor V, and we know that V is L di dt. That's our differential equation. In the phasor domain, we have to write that the V across the inductor is the real part of the phasor across the inductor, and the current through the inductor is the real part of the phasor, written out like this. And so if we use this and this together, we can say that the real part of the phasor is L times the time derivative of the real part of the phasor for current. And if we take this and combine and get rid of the real part and the j omega t part, we can see that the phasor for voltage is j omega L times the phasor for current for an inductor. And once we get this phasor equation, we can calculate the impedance. So Z is always going to be V, the phasor for V over the phasor for I, and so here it's j omega L. So it has the inductance L, it has the frequency omega, and J is the complex number, square root of -1. So this is the impedance, and we'll use this going forward, just like we use resistance. Doing the same thing for capacitors, we have I is C dV dt, So it's the same kind of differential equation as the inductor, but V and I change places. And so we could go through the same steps, but it's fairly easy to see that here I, the phasor for I, is j omega c times the phasor for V, because c dv dt, when we take the derivative, we get a j omega comes out. So here's our j omega from the derivative, the c from the equation, and we get our basic IV equation for a capacitor. And using this, we can solve for the impedance of the capacitor, ZC, V over I, so 1 over j omega c. It's a complex number, 1 over j omega c for impedance for a capacitor. So we're going to use this over and over again. So it's good to have this handy. Here's where we are. We have the time domain, the phasor domain, and impedance. So we've gotten impedance for a resistor is R, impedance for an inductor, j omega L, impedance for a capacitor, 1 over j omega c. These are complex numbers, and so we can write them either in the polar form or the rectangular form. They're already kind of in the rectangular form, so R plus 0 times j, because it's entirely real, for the impedance of a resistor, 0 plus j omega L for the inductor, entirely in the imaginary axis, and 1 over j, if you multiply the top and the bottom by j, you get a j in the numerator and a j squared in the denominator, and j squared is -1. So you can move the j from top to bottom if you flip the sign. Try that yourself if you're not sure, because it's a very common trick. But put the j in the numerator and we flip the sign there. So j over omega c, 0 minus j over omega c, is the rectangular form for the impedance of a capacitor. Once we have this a plus j times b kind of rectangular form, we can use those equations from the last lecture and find the polar form. Sometimes this one form is easier to use than the other. For addition and subtraction, we like rectangular. For multiplication and division and going back to sine waves, we like the polar form. So R with a phase of 0, omega L with a phase of 90, because it's straight up the y-axis, and omega c with a phase of -90, because it's straight down the y-axis here. So if you're not sure, use those formulas and calculate these back and forth and make sure you see it. And here's the hand sketch, the important things. It's the same thing, impedance for a resistor, inductor, and capacitor, polar form and rectangular form, and also sketched out. So here we have on the imaginary axis on the y-axis and the real axis on the x. Resistors are straight out on the x-axis, entirely real, value of R. Inductors are entirely imaginary, positive omega L on the y-axis, so phase of 90 degrees. Capacitors are entirely imaginary, but they have a negative imaginary component, so -90 for the phase, and an amplitude of 1 over omega c. So these impedances are the key to our solutions going forward. All right, so let's try this on a circuit. We are going to analyze this RC circuit, and we have a sine wave for V. So Vs is 12 times sine omega t minus 45 degrees, units of volts there. And we're trying to find the steady state function for I of t. So this is a sinusoidal steady state. That means phasors. We're trying to find the current as a function of time, and we have values for the resistor, squared of 3 kiloohms, 1 microfarad for the capacitor, and omega is 1,000 radians per second. All right, so here is a big graphic here that walks us through the steps, and we'll see all the steps. But the first step is going to make sure we're doing cosines and not sine waves. We'll use a trig identity if we need to make everything cosine, so we're on the same time domain basis. Then we transform everything to the phasor domain. That gets rid of differential equations, and we can then solve in terms of impedances, just like we would with resistors, and solve for whatever we need to find, and that will give us a phasor for our solutions. and then we have to transform them back to the time domain. So this is what we do. We transform, solve, and then transform back. So the first step here is, because we started with a sine wave, we want to make it a cosine wave. So if you remember from the previous lecture, we can just take an extra phase of -90 and switch sine to cosine. So our voltage is 12 cosine omega t minus 135 degrees. And here's where we're mixing the units. This is degrees, this is radians per second times seconds. Very common, it's okay. You'll get used to it. And so then we want to transform the circuit into the phasor domain. So here our voltage, which is our cosine wave now, we can just take the amplitude of 12 and the phase of -135 and write them down. 12, this is the little angle symbol, phase of -135, or the book uses this exponential just to kind of remind us of where it comes from. Amplitude of 12 and a phase of -135, and the E and the J just kind of float along like this angle symbol. Either way. If we want to put it in rectangular coordinates, then we can use this polar form and convert it to rectangular. You might have a button on your calculator to switch from polar to rectangular, a graphing calculator, or you can use the equations. The amplitude times cosine of the angle gives us the real part. The amplitude times the sine times j, there's a 12 that's missing in here, gives us the imaginary part. Okay, so then the next step is to do our circuit analysis in terms of impedances. So we have a resistor and we have a capacitor, and we treat them the same. That's the great thing. No differential equations. They're just things with impedance. Often we'll redraw the circuit with just boxes there. Going around this loop, the voltage across the resistor plus the voltage across the capacitor has to equal the voltage across the source. So that's Kirchhoff's voltage law. And then Ohm's law is now V equals IZ. So the impedance of the resistor times the current plus the impedance of the capacitor times the current equals the voltage. So just what it would be if they were all resistors, but we use Z instead of R. The impedance of the resistor is just R. The impedance of the capacitor is -J over omega C times I. And then we had V from the previous step, 12 with a phase of -135. So no differential equations, complex numbers, some weird stuff, but better than differential equations. So we can do node analysis in general, mesh analysis in general, Thevenin and Norton's, everything, but in terms of impedances. So that's where we're going with more examples coming up. Then we solve. So we're trying to solve for I. So we divide through by this impedance of both components. And this is our voltage, so V over Z, the total Z. And remember that R was 3 kiloohms, C is 1 microfarad, omega 1000 radians per second. And so we can't solve this very easily in the way that it is with a polar on top and a rectangular on the bottom. So we have to decide one or the other. So here I'm going to put the polar into rectangular and use MATLAB. So here is a MATLAB script. So V, which was 12 with a phase of -135, in rectangular is 12 times cosine D, so I can use degrees, -135, plus J, square root of -1, times 12, amplitude sine of -135. So we get this rectangular form from the polar form. And then Z has got R and omega and C, so it's the square root of 3 kiloohms, so times 1000, and then minus J divided by 1000 is omega, and C was 1 microfarad, so 1 times 10 to the minus 6. Make sure you put your parentheses in here. There are many common mistakes from not dividing these things properly. That'll give us our Z in rectangular form, and then we can use MATLAB to solve for the current, V over Z, and we get it in rectangular form. We want to go back to polar form, so we can go to cosines, and so you can use the real part squared plus the imaginary part squared under the square root to find the amplitude, but in MATLAB the absolute value function does that for you. So ABS of the rectangular, the complex number I, gives us the magnitude of 006 amps. And in MATLAB, there's an angle function for complex numbers. So if this is a complex number, you can find its angle, and it does atan2 and everything. So I like to use this in MATLAB. The angle of the complex number, it'll be in radians, so I multiply by 180 over pi, and we get negative 105 degrees. So our final answer is the current as a phasor has this rectangular form or this polar form, 006 with a phase of minus 105. If we wanted to do this by hand, it's probably easier to do this division. This is where we started the last step in polar form. So leave the 12 with a phase of minus 135 on the top and convert this to polar form using the equations for rectangular to polar transformation. So here again we would write z in rectangular form because that's how it started, with the real part and an imaginary part, and then find its angle using the angle function in MATLAB, negative 30 degrees, and its amplitude using the ABS function is 2000. So we can write 2000 with a phase of minus 30 is the same as the total impedance here. And then we can divide these by hand. So 12 over 2000 gives us our 0.006, and negative 135 minus negative 30 gives us our negative 105 for phase. So if you're doing them by hand, dividing is easier in polar form. And we get to the same answer as the previous one. You don't have to do both ways, but one or the other. And just a reminder, here are the equations for going from rectangular back to polar and polar back to rectangular, and the sketch is very helpful in case you're not sure of your math, if you can kind of sketch it out when you see the components. Which quadrant are you in? Is it really big? Is one of them really big compared to the other one? Then you're maybe along one of these axes. So when you're back somewhere like this and you have 1.73 times 10 to the 3 and negative 1, you're going out over here and down, so we're expecting something in this range, which is why negative 30 comes out. So it's good to get a sense for these. Okay, so we have a polar form for the current, which is what we wanted. So we're actually done. We've done the math, but you can't leave it here if they want a function of time. So we have to take the 6 milliamps or 0.006 amps and the phase of negative 105, and just template them back here. It's going through all of this real parts, but really we just take the amplitude and put it here. We write cosine omega t, and we take the phase and put it right there. And this was in milliamps because it came from the book in milliamps, or you could do 0.006 amps, either one would be fine. So just don't forget this last step because it just is an easy transform back. So looking ahead, we'll be doing more of this, but impedances, they work just like resistors. So all of the techniques we had for resistor circuits like node and mesh analysis, Thevenin and Norton, work exactly the same with phasors. That's why we like this so much. The one exception is the numbers are complex numbers rather than real numbers. But impedances in series add together. Impedances in parallel, it's the 1 over equations. Ohm's law, V equals IZ. So impedances and resistors have basically the same equations. All right, so we'll look at more examples coming up, and hopefully you're keeping up with the math and enjoying this alternative to differential equations. See you in the next video.